Hey everyone, in my GAN series with PyTorch, today I'm going to do BicycleGAN, and officially it's known as Toward Multimodal Image-to-Image Translation. Hello, my name is Rohan-Paul and very welcome to my computer vision and deep learning YouTube channel. Let's get started. One more thing, that over the next month, I will do many GAN or Generative Adversarial Network implementation from scratch with PyTorch. So do subscribe, because you hitting the subscribe button is what keeps me motivated to do this. Let's start. And here I'm looking at the original paper of BicycleGAN. It's called Toward Multimodal Image-to-Image Translation. And the paper was released in October 2018. Now, let's come to the important topic of the paper. So, I have highlighted all those important areas. So, BicycleGAN consists of two components. One is Conditional Variational Autoencoder GAN or CVAE GAN, and the next one is Conditional Latent Regressor GAN or CLR GAN. And what exactly they are? So CVAE GAN is one approach where it's about first encoding the ground truth images into the latent space, giving the generator a noisy peak into the desired output. In using this along with the input image, the generator should be able to reconstruct the specific output image. And then under the CLR GAN, that is the second part of our BicycleGAN, the approach is about first provide a randomly drawn latent vector to the generator. In this case, a produced output may not necessarily look like the ground truth image, but it should look realistic. An encoder then attempts to recover the latent vector from the output image. This method could be seen as a conditional formulation of the latent regressor model. And finally, in the BicycleGAN, we combine both these approaches to enforce the connection between latent encoding and output in both directions jointly and achieve improved performance. So all these will become much more clear when we start implementing them actually with PyTorch in a moment. But let's move ahead in the paper to look at this super important pictorial representation of BicycleGAN. And this image tells us all that we need to know about BicycleGAN. Here, A and B represent images in two different domains, and B hat is the fake images produced by the generator G, and D here is obviously the discriminator, and obviously this letter E represent the encoder. And we can see there are two parts in the whole BicycleGAN architecture, which is the first one is CVAE GAN and the second one is CLR GAN. So in the first part, that is CVAE GAN, it encodes the ground truth image B into the latent space using this encoder E. Then the input images A and the encoded ground truth images, that is the latent vector Z, are passed into the generator, that is this G over here, which produces the output image or the fake image that is represented by B hat. That is, the generator attempts to map the input images A along with a sampled Z back into the original image B. So overall, the flow in the CVAE GAN part is from B, we start with B, then we move to these latent vector Z, and then finally to B hat, that is a fake generated images from the B domain. And now the second part of BicycleGAN, that is CLR GAN, and here a randomly drawn latent vector along with input image A is passed to the generator G, and the generator then produces these B hat fake images, and these B hat may not look like the ground truth image B, but it should look realistic. Then the generated output, that is B hat, is passed through to the encoder E, and the encoder tries to regain the latent vector, that is Z, from these output images. So the overall flow in CLR GAN is we start with Z, then move to B hat, and then finally try to get Z back again. The objective function of BicycleGAN is a combination of CVAE GAN and CLR GAN objectives, and they actually detail all the equation for the loss function down here in the paper. Yeah, right here. So the first part of the overall loss is the CVAE GAN loss, and the equation for that is this one. I have put a red border around it, and there are three parts to this loss. The first one here is the GAN loss, or the VAE GAN loss. The second part is my L1 loss, and the third part is the KL divergence loss. And these two parameters, that is lambda and lambda KL, they are hyperparameters that we need to set during our training. So that was the first part of the loss, and now moving to the second part of the loss, that is which comes from the conditional latent regressor GAN or CLR GAN, and the equation of that one is given here. So this equation has two parts to the loss: the LGAN loss and also the loss for the latent vector. And this will all become much more clear when we implement this in a moment. And then from these two losses, we have our final hybrid loss, that is the total loss for our BicycleGAN, and that's just the addition of those two different losses. And this is that final equation of my BicycleGAN loss. So that was a loss. And just one more important point from the paper, which is about the network architecture details. For generator, they use UNet, which contains an encoder-decoder architecture with symmetric skip connection. And for discriminator, we use PyTorch. This is exactly the same that we used in CycleGAN paper as well. There as well, we used 70 by 70 PyTorch. So here, what they are saying is that we use two PyTorch discriminators at different scales, which aims to predict real versus fake for 70 by 70 and 140 by 140 overlapping image patches. All right, with that introduction about the architecture, let's start the actual implementation. So first, I'm just importing all the standard imports, connecting my Google Drive, and then declaring all my hyperparameters. And what are my hyperparameters? Their epoch, total number of epoch, batch size I'm keeping at 8, and then learning rate 0.002. Then number of CPU 8. You can of course change this. Image size I'm keeping at 128. And one important thing to note is that here I will be using for the dataset the UC Berkeley CycleGAN dataset called MAPS. So obviously I will give this link of this dataset in the description, but if you do a quick Google search, you will find it very easily because it's a very popular dataset, and it actually comes under these pix2pix dataset of ucberkeley.edu. So this is the dataset that I'm talking about, maps.tar.zz, and it's 239 MB around. And in that dataset, all the data are of 1200 by 600, that is width and height respectively. But here for this particular video, I will transform all the images to be of 128 by 128, and that's why I have a hyperparameter here called image size. Number of channels will be 3 latent dim. This is one hyperparameter which will be required to create our Z vector, which will be passed to the CLR GAN as the input randomly generated vector. So that number I'm keeping at 8. And number of critic 5. I don't think I need this here. This mainly comes from CycleGAN. Yeah, I think I can delete that. We'll see that about in a second. And then these are my hyperparameters as mentioned in the paper: lambda KL. Then I also need lambda pixel. All right, again sample interval, this is only required for visualizing or plotting my epochs training. And I'm keeping all my dataset in my Google Drive, hence this image root folder is referring to my Google Drive folder directory. And the next cell has image dataset class, which will do its normal job. That is, it will fetch the images to be passed to my data loader. So this get item method actually implements that job of getting the images by index. Now, couple of standard things I am doing here within the get item. The first one is for getting the image by index. I am making use of this little code here using the modulo operator of Python, that is this percentage symbol here. So what basically it will do is a modulo b means a divided by b, and then the remainder of that division is returned. But in this case, for example, my index, say for example it's 5 and I have 100 images, so 5 modulo 100 will return you the 5. And why I'm doing this, my actual target is to find the indexed item in the list based on the length of the variable in the list. That is, I just don't want to get the, I could have directly put the index on the files list, but in that case, if my index number is more than the length of the file, that would create problem, that will generate an error. So I had to find some way so that the index number, the indexed item is returned based on the length of the file, and if my index number is more than the length of the file, none will be returned. So that's why I'm making use of this. And then in this block, I'm just taking my original the width and height of the image and then cropping the image to make image E and image B. Image A and image B. And the crop function takes 4 coordinates as the argument. So those coordinates are the images left corner, upper corner, right corner, and lower corner, and that's what I'm passing here. So for my image A, I'm taking 0 0, then W by 2 and H. For image B, I'm taking from W by 2 and then 0 WH, that is which, and they represent, this is left, this is upper, this is right, and this is the lower corner. And in this part of the code, I am only implementing a horizontal flipping of images based on a randomly generated probability. And the probability is determined from this line. If np.random.random is less than 0.5, then horizontally flip image A and image B. And for that horizontal flipping, I could have used some augmentation tools both in the image module or maybe OpenCV, but I'm making use the most simple, the most from scratch implementation of horizontal flipping. That is, I'm flipping these width dimension of the image. So these notation slice -1, what this will do is all item in this dimension will be returned, will be reversed. So basically, if you have a list A and you want to reverse all the item in the list A, you just do this, that A, then within the square bracket you pass a slice -1, and that what that will return is all items in the array reversed. And here in these two lines, I'm doing the exactly same thing, but I'm just doing only for this middle dimension, and in this case the middle dimension represent my width of the images. And then finally, I'm just applying the transforms on both image A and image B, and then returning a dict which has a key of A and B. And this transform will come from my arguments to my image dataset class, and this transform you will define in the later cells. And also one point to note here, I have put that in the comment here indeed, that why I did this horizontal flipping is because similar horizontal flipping was actually implemented in the official PyTorch BicycleGAN repository here in this link with this kind of code, that there they had a flip method which will apply a transform which is image.flip left to right. So that's pretty much what I'm doing, but I'm doing it from scratch. And then in the next cell, I just have a couple of two super small methods, utility methods to help in my plotting. these methods are kind of obvious, and also the same kind of methods I've used in all my previous GAN videos, so I have explained them in detail over there, so you can just have a quick look. Basically it's just nothing. The IM show just takes a image tensor, then transpose that image tensor to be compatible with matplotlib with this line of code, and then just plotting that image with plt.show. That's all. And visualize output as well. It takes a path and the x and y and plots the image, and this visualize output we will use while I am going to plot during the training loop. Another quick point on this IM show method, that why I am doing this particular thing, image by 2 plus 0.5, because it's actually denormalizing. So I put the notes here again. That is, and I have taken these guidance from the PyTorch forum indeed, that during normalization you do z equal to x minus mean divided by sigma, and now you have to reverse this process. So when you reverse it, your x will become z into sigma plus mean, and that's what I'm doing here. And then my actual data loaders, again very standard pipeline of workflow that you will see in all my previous GAN videos, or for example any PyTorch projects for that matter, with the image dataset. So this is my transform, that very simple resize, to tensor and normalize. Only these three transforms I'm applying on the images. Then this is my actual data loader, and I'm making use of the data loader module of PyTorch, and then I'm invoking within data loader this image dataset class that we have previously defined. That only takes the image root folder and the mode, whether you are in the training mode or test mode, and the transform, and also batch size, shuffle, number of workers, etc. Very simple. So that will give me my train data loader, and that's exactly what I need for my entire training. The next cell here is just a little visualization code. When you run this, you will see some images plotted properly here from the training dataset. And now from here, the actual network implementation starts. So first, this method wait init norm. Here I'm just initializing, I'm just mentioning the strategy to initialize my weights based on whether it's a conf layer or batch norm 2D layer. And then we have to implement unet, both unet down and unet up. Because as per the paper, they say that for generator we use unet, which contains an encoder decoder architecture with symmetric skip connection. In the encoder, the size of the image gradually reduces while the depth gradually increases. So that's what this unet down is doing. So unet down is that encoder part, and here the depth will gradually increase. And so the depth increase means is outsize. This actually represents my output channels, number of output channels in my conf2d, that will gradually increase. Otherwise this is a very simple neural network structure. That is very much what I'm doing. I'm just declaring these layers, which is a nn.conf2d. Insize and outsize actually represent the number of input channels and number of output channels. 3 is my kernel size, stride is equal to 2, padding 1, bias false. And then depending on whether this normalize is true, I am adding batch norm 2D, else I am not adding that. And after the batch norm 2D, I am only adding this leaky ReLU, and then that's it. Finally, the self.model is just this entire nn.sequential, and to that I'm passing these layers. And the forward function just takes this input variable x, passes that through the model, and that's my return. That is the model output. Now note that in UNet, it's a fully convolutional neural network, that is only contains convolution layers and does not contain any dense layer. And that's the reason UNet can accept images of any size. And then the UNet up part, which is a decoder part, and here the image gradually increases and the depth gradually decreases. Depth again means that is the outsize. So here again I will be the first layer will be upsample, and I'm upsampling by a scaling factor of 2, because this is where I have to gradually increase the image size and decrease the depth. So this upsampling is very much required. And then conf 2d, in size, out size, that is input channel, output channels, otherwise everything remains same. And finally batch norm 2d and ReLU. And forward function takes the input x and skip input, and then takes the input x through the network, and finally it concatenates x and the skip input and return that value. Sorry. And then the all important generator network of my BicycleGAN. It starts with these fully connected layer, self.fc, that's a linear layer, and it takes the in features as my latent dim, because the generator in BicycleGAN will be fed both the actual input images and also the latent dim, the z vector. So the linear layer is actually representing that is in features latent dim, and then it also takes the height and width of my image shape, and this image shape is my original input image. And here we already have made the height and width to be 128. And then this next block is just the repeated invocation of unit down and unit up. So for the entire encoder part, I am invoking unit down, where my depth gradually increases and the image size decreases. And then unit up block, where the depth gradually decreases and the image size actually increases. And then the final layer is just an upsample and also another conf 2d. So I have got three blocks, or you can say that is the FC, all these unit, and then the final layer. And the forward function or the forward method will just implement all these structures. So it will start with self.fc, that will take my z, and that will be reshaped properly. That is z will be reshaped to z.size 0, then 1 self.h, self.w. H and w here is 128 by 128. And then the first invocation of the encoding part with my unit down is this line. But note here that here I am implementing torch.cat, because I have to concatenate two vectors, which is the first one is image vector x, and also the z vector, that is the noise vector, which will be concatenated and passed to my first unit down. And then all these is just the repeated invocation of those, that is the output of the previous layer goes as an input to the next layer, and so on. And then u6 becomes my final output from the entire unit implementation, and that u6 goes to the final layer, and that's my output from the generator network. So that's my generator. And then my very important part of BicycleGAN, which is encoder. And the encoder will mainly required for calculating these mean and log var, which will be required for implementing this reparameterization trick that is normally used in VAE. So if we go back to the paper, they in the implementation details they say that for the encoder E, we experiment with two networks. One is eCNN, which is a CNN with few convolution and downsampling layers, and two, eResNet, which is a classifier with several residual blocks. So I am going with this ResNet for doing my encoder architecture. And just remember, going back to the original architecture image where that encoder is needed. So this is the architecture. This part is for the CVAE GAN and this part for CLR GAN. So under the CVAE GAN, we use encoder to here, and then the encoder takes this actually produces these z vector, And also for the CLR GAN, after B hat is produced, that is the fake image is produced from the generator, then we take that fake images through the encoder to get back my Z vector. So this is where the encoder is needed. So let's go back to our code. And I will talk about this very important topic in VAE, which is reparameterization trick, where we have to modify the Z vector so that the back propagation can continue with stochastically generated Z vector in a moment. But let's just go through this quickly through this encoder method, and then in a second we'll talk about the reparameterization trick. So the encoder, the init function, I have these pre-trained model ResNet 18, which I brought in from Torch Vision, and from these pre-trained model I have to exclude the last 3 layers. So let's check what are the layers I have in my ResNet 18 pre-trained model. So I'm just going to a new Jupyter notebook and pasting this code. It will just print the various child and with the child counter variable, all the different children that ResNet 18 model has. Let's run this cell, and I have these starting from child 0 up to child 9. And now I am going to check out what are these children actually. So first let's just check out with this code the last one child indeed. So I'm just making use of the slice notation with -1 and then slice. That will just bring me the last item from a list. Let's run this, and I'm getting the last layer as a linear layer with in features 512, out features 1000. Let's check out the last 2 layers. And now I have the adaptive average pool 2D. I want to exclude both of them. Let's check out last 3 layers. All right, so now I have a batch norm 2D, relu conf 2D, and then my adaptive average and linear layer. So I want to exclude these last 3 layers, and so in this line what I'm doing is I'm bringing in the slice notation before the -3, which will include everything except the last 3 items in the array. And here my array means the whole list of all the layers, and that's why I'm using this list method here. And after extracting all the layers except the last 3 layers, then I am only adding average pool 2D after this in this line. And then I from this network I need to, from the last 2 layers of these encoder network, I will define my mean and the log var variable. So that's how I'm defining it. That is output is mu and log var for reparameterization trick used in the VAE, and both the mu and the log var is assigned the same value, which is the encoder's last layer output. And the forward function is just implementing this network structure, that is to the feature extractor object. I'm passing the input image, then the output from that goes to the input from my pooling layer. Then I reshape it with view, and so my final mu and log var becomes this final output. And that's what I'm returning from the forward function, which will actually become the return value from the entire encoder block. And that's what I'm going to use to calculate my reparameterization numbers. And then my discriminator block, and I'm naming these multi-discriminator because it will be used as a discriminator for the different parts of my BicycleGAN architecture, that is both for the VAE GAN and also for the CLR GAN. And this is pretty easy. I'm just first defining a discriminator block which will add a conf 2D to a layer, and depending on whether the normalize argument is true or false, it will also add a batch norm 2D and a leaky relu at the end. So this discriminator block is invoked multiple times to build the entire network of my discriminator through these looping methodology here. so where I'm looping over a range of 3, and for each time I am adding an nn.sequential with the discriminator block, and the channel numbers, the input channel and output channel is defined as below, and you can see that the output channel goes on increasing to be ultimately 512 here. And okay, and within the discriminator class I also have these compute loss. It is just a simple MAC loss calculation between the ground truth and the predicted output variable. And finally, the forward method in the discriminator class just takes the input x, takes that input x through the entire network of discriminator, and finally gives the output from that. Oh, another quick thing that I added these nn dot average pool 2D to downsample my input. So few points to note here in the discriminator, that this module list, this nn.module list, it is just like a Python list. It was designed to store any desired number of nn.modules. It may be useful, for instance, if you want to design a neural network where the number of layer is passed as an input. And that's what I'm doing here. Note that here when I'm passing nn.sequential, the discriminator block, then I'm using this asterisk. And what this means is that I'm not passing the list of the discriminator block directly to the nn.sequential, but rather the content of the discriminator block layers is passed. And that's why I'm doing these nn.sequential and then an asterisk and then my discriminator block instead of without the asterisk. And here in this line, self.models equal to n.module list, you can ask that why not, if module list is just like a Python list, then why not instead use a normal Python list? And the answer is that if you use a plain Python list, the parameters won't be registered properly, and in that case you cannot pass them to your optimizer using models.parameters. And because I use this nn.module list, which is just like a list, note how I have to use these list element from the module list within my forward function. So here basically I am running a loop through each of the layers within my models, and then I am passing to that model layer these input variable x, and that gets appended to my outputs array or output list. And finally from the forward function, these outputs array is being returned. So here in this line, it's the most important one, that to each element of the outputs array I am passing the output of these specific layers output. And what are these specific layers? This is each of these discriminator block. And also note that in the compute loss method, how I have to use these forward function. So I have to do self.forward x. All right, so both my generator, discriminator and encoder is defined, and now I'm almost ready to do the training. So in the next cell, I'm just initializing the model, the buffers, and DVAE and the DLR. So here generator and encoder object, to that I'm passing the latent dim to both of them, and latent dim comes from the hyperparameter, and input shape is just the input shape of my input image, which is hp.channels, which is 3 because it's all our color images, then hp.image size and image size, and we set this image size to be 128. And then I am passing all these variables to my CUDA to use GPU, and also initializing weights with the apply method. So for each of my generator, and then the discriminator for the VAE part and the discriminator for the CLR part, I am making use of the apply method to initiate my weights initially. And then this cell next is a simple utility function. So this method will basically work on the validation set, and it will take a sample of images from the validation set, generate a fake images, and then returns a path of the fake images to be later plotted. So this entire sample image method will just be implemented to visualize after my training is done, or rather during the training of epochs, so that I can continuously see the how my training is working on the validation set. So this path variable you have to define, and it can, here I'm defining it to be like this because I'm running this in Google Colab, and the content directory is the default path in your Colab session. And then I'm just taking images with this line from my validation data loader. So this next and iteration will continuously give me the next and next and next batches when this loop will run. And then I'm creating these fake B images by passing the real A and the sample Z to my generator. And then these fake images are horizontally concatenated, and then the concatenated images are saved with the save image method of Torch Vision. The save image just saves a given tensor into an image file, and then finally I'm returning the path from this method, and this path will be passed to another method that we have defined earlier called visualize image or something like that. And then visualize image will just plot or show the images in this path. So that's how it will work. And then in the next cell I am just initializing all my optimizers, that is one for the encoder, one for the generator, then one for the discriminator VAE, and another one for the discriminator LR, and declaring or initializing this tensor variable to be to use my CUDA if that's available. All right, now the very important part in a VAE called the reparameterization trick. And the reparameterization trick is about modifying my stochastically generated Z vector by learning two additional vector, mu and sigma. And then the modified Z vector will be defined by these expression. That is, the new modified Z is equal to mu plus epsilon multiplied by sigma. And here epsilon is a very small number which is sampled from a normal distribution n01, that is a normal distribution with 0 and 1 as a mean and standard deviation respectively. And this multiplication symbol here actually expresses the element-wise product between epsilon and sigma. So if an input data point is to be mapped into a latent variable Z via sampling, it has to follow these equation, that is a modified Z equal to Z mean plus epsilon into STD. And here the standard deviation is defined as torch.exp, and then within bracket the log variance of Z divided by 2. So we'll come to this expression in a second. So basically these reparameterization trick for Z has two mathematical expression. One is what we just saw, Z equal to Z mean plus epsilon into STD, and another one that you will see in many papers is this expression, Z equal to mu plus epsilon into e to the power 0.5 into log var. Actually they are just the same, because if you simplify this part, that is equal to 0.5 log variance, that will become E log then variance to the power 0.5, which will become variance 0.5, and that's my sigma. So basically this expression and the first expression that we saw initially, that is the Z equal to Z mean plus epsilon into STD, both are just the same. And on the elements of these reparameterization equation, both mu and log var is coming from the encoder's latent space. And also we learn the log of the variance instead of just the variance, because the variance of a random variable is constrained to be positive. That is, this term var needs to be positive only. And so if we were to try to learn only the variance and not the log of the variance, we would have to constrain somehow the output of the neural network to be positive, which may not be always the case. So a simple way to go around this problem was to learn the logarithm instead of the variance. Thereby we are no more constrained to be the output to be a positive number always. And also, why don't we learn the log of the standard deviation directly? Why do we take the square? That is, why do we take the variance? That's because it doesn't mathematically really doesn't make any difference, because log of a square term is just the 2 log of that term. So what I'm meaning is this, that is log of sigma square equal to 2 log sigma. So learning one is as easy as learning the other. And normally, just by practice, in most mathematical paper, most machine learning paper, we use variance in this kind of situation. And the fundamental question, that why do we need reparameterization at all? That's because to implement encoder and decoder in a neural network, we need to backpropagate through random sampling, and that is a problem because backpropagation cannot flow through random node, and z here is my random node, or it is generated randomly or stochastically. So to overcome this problem, we modify z with the reparameterization trick. So overall, this term epsilon allows the mean and log variance vectors to still remain as the learnable parameter of the network while still maintaining the stochasticity of the overall system. Alright, that's all the theories behind reparameterization, and now the simple function to implement it. So this is my method that will take the z mean and z log var as argument, and this will give me the modified z after applying the reparameterization. So all I'm doing, my std is just torch.exp z log var by 2. That's following this this equation here that we discussed, and then I create a sampled z from np.random.normal from a normal distribution which has a mean of 0 and std of 1, and this just mention the shape of the normal distribution. And then my modified z will just become z mean, which comes from the argument, plus sampled z into std, and std is my log var by 2, that is e to the power log var by 2, and that's my modified z is a return value from my reparameterization. And now we will see the use of these during the training, but let's now move forward for the training. And here starts my training, and just like all GAN training and all my previous videos on GAN, we have 2 loops here. The outer loop is for each epoch, and the inner loop is where all the actual work will go on. And this inner loop will start with this line where I'm fetching batch by batch data from my train data loader. And this is just my model input from my train data loader, real A and real B. Remember, my train data loader returns actually a dict where the keys are A and B. Alright, so now first my generator, train the generator and the encoder. And if we go back to our original paper, we remember training generator, the training CVAE GAN starts with this part where the main difference with the normal GAN is that instead of paired generator and discriminator, here in BicycleGAN, the model uses generator and VAE encoder. So this E is my VAE encoder and G is my generator. And again, from this figure, we can see that A and B are images in 2 different sets. And in CVAE GAN, it first encodes a ground truth image B into the latent space using encoder E. Then input image A and encoded ground truth images, that is the latent vector Z, are passed into the generator G, which produces the output image B hat. That is, the generator attempts to map the input image A along with the sampled Z vector back into the original image B. So let's implement that in our code. So in my CVAE GAN, first this is the standard step, 0 grad. I am making both the optimizer, cleaning up the slate, and then I am bringing in my encoder and passing it real B, which will give me mu and log var. And then that now that I have the mu and log var, I can pass them to the reparameterization function to generate my encoded z, and then my fake b will just be, that is the real a, and this encoded z is passed to the generator function that produces fake b. That is, in this image, to the generator I give both the encoded z vector and also the real a to produce b. And now that I have the fake b and also my real b, I can calculate one part of the loss of BicycleGAN, which is this line. This is an L1 loss between fake b and real b. And if I go back to the paper, the loss section, so under the CVAE GAN, so this is the loss or objective function of CVAE GAN, and what I just calculated, this is this L1 loss, L1 VAE G and E. So that's my L1 loss, and now I also need to calculate two more losses, that because our objective function has three elements. This is the first one. This is the normal VAE GAN loss, then the L1 loss, and the last part is a KL divergence loss. So for my KL divergence loss, I am doing that in this line, which is 0.5 into torch.sum, then within the braces torch.exp log var plus mu square minus log var minus 1. And how I am getting this formula, you can check that in this Stack Overflow question. It explains it very well. Let's go there. So here is that page in Stack Overflow, and the question is, how is KL divergence in PyTorch code related to the formula? So the original formula is this. If you go to Wikipedia, you will see this is how the KL divergence is defined for VAE, that is variational autoencoders architecture. But how come this formula actually boils down to this one? And this is exactly my formula that I have used here. They are taking the minus sign at the very first. I do not have that minus sign because I have making the corresponding adjustment within the braces. So the reason that the answer gives very beautifully, that if you actually simplify these matrix multiplication and all these traces calculation, etc., then you actually end up with this formula. That is the whole KL divergence is equal to half of sigma 1 to k, and then within the braces all these elements go sigma I square mu y square minus 1 minus log variance. And if you that's exactly what I'm implementing in this formula, and that's the kind of way that many repositories which deal with VAE GAN or BicycleGAN or CycleGAN or KL divergence in general have implemented this formula. And after this KL divergence loss is calculated, the last loss that is still due in my VAE GAN is this first element of the loss function, which is a normal GAN loss, and that's just my this line. And this is just making use of this compute loss that we have defined within the discriminator class, and it's just the MSE or mean squared error between model output and scalar ground truth. All right, so there completes my VAE GAN part, and now the next GAN part within the generator training is the CLR GAN or conditional latent regressor GAN. So coming back to the paper, here is the CLR GAN part. So here in the second component of BicycleGAN, a randomly drawn latent vector, that is NZ, along with the input image A, is provided to the generator. The generator outputs B hat may not really look like the original B, but it should look realistic. Then the generator output is passed through the encoder E, and the encoder tries to regain the original latent vector Z. So here the flow is from Z to B hat back to Z. Hence, to generate B hat from the Z vector, first define my sample Z. So this is my sample Z. I'm again using np.random, and for the size, this Z vector needs to be a 2-dimensional tensor of batch size and latent dim. So the first dimension should be batch size, which is 8 in this case, and latent dim is also defined to be 8 in my hyperparameter at the very top of this notebook. So that's what I'm passing in my sample Z creation code, that is to my np.random.normal. Real a.size, the first dimension is 0, and that's my batch size, and that's 8, and hp.latentDim. So if you print the sampled Z size, that is with this line, I have commented this out here, so that will produce torch.size 88. And actually, if you print the entire sample Z, that is with this line, again it is commented out, it will produce this kind of output. So it's this tensor that you can see here. It's a 2-dimensional tensor with a size of 8 by 8. That is total number of rows are 8, and total number of columns are also 8. And obviously, before passing these real a.size, etc., I had to check the real a size as well. So here in this line that is commented out, I actually printed the size of real a, and that outputted 8 by 3 by 128 by 128. It's again, the format is batch size, channel, height, width. Alright, so now I have sample Z, I have real A, so I can produce my fake B, that is this B hat, and that's simply this line. That is to the generator, I pass real A and sample Z, that will produce fake B. And now I can have my loss CLR GAN, that is the loss of the CLR GAN, that's simply dlr.compute loss. To that you pass this fake B that is just generated and the valid vector. And remember, valid vector we have defined at the very top of the training, which is valider all 1. So now I have all the loss components both from my VAE GAN and also CLR GAN. So I can calculate the total generator losses. But let's quickly go back to the paper to check this final formula here for the hybrid model, that is for BicycleGAN. Total generator loss will be defined by this formula, and it is just the addition of the losses for the VAE GAN and the losses for my CLR GAN. To that, I also have to include these hyperparameter, that is lambda, lambda latent, and lambda KL, and which are all defined in my notebook, and the very top where the hyperparameters is defined. So this line is my total loss for the generator, and that's just loss VAE GAN plus loss CLR GAN plus lambda pixel multiplied by loss pixel L1 VAE, and again lambda KL multiplied by loss KL. And then my loss is there, so I can apply my backward and step to do the back propagation and update the weights. And now I also have to do the next part of the CLR GAN, which is this part, that is the generated output is passed through the encoder E, and the encoder tries to regain the latent vector from the output images. That is, these B hat will be passed through E to output Z, and that is this part. That is, to the encoder I passed the fake B that we just created in the previous step. Where is that? Yeah, fake B that was created in the previous step in the CLR GAN. So this fake B now is passed to the encoder, and encoder will give me what? The mu and log var, and I put the log var here just as underscore because now I don't need the log var part now, but I need the mu part because I have to compare this mu with the actual sample Z. So in the next line I'm doing just that, which is actually my L1 loss that I'm naming it as loss latent, and that's just the lambda latent multiplied by MAE loss, which is actually calculating the L1 loss between mu and sample Z. sampled Z is what we created in this line here, that is within the CLR GAN, the very first step. So this is just so here the encoder, where is that? Encoder is just try to recreate or reconstruct these original sampled Z, and obviously there will be a loss, and that loss is what we are calculating in this line. And again, after that loss calculation, just do the back prop and the step to update the weight. And there, here my generator training ends, and now my discriminator training. Let's go there. First step, as always, 0 grad. And training the discriminator in BicycleGAN is rather very easy. It's just 2 small steps. So here, first I'm calculating the DVAE. That is, in this part I'm calculating the CVAE GANs part of the discriminator. So I have DVAE.compute loss. To that I'm passing real B and valid, and also I have to do the fake B and fake. And sum both of these discriminator losses. That's my DVAE loss. Then do the back prop and step on this, and then do the same for my CLR GAN part. And here again start with 0 grad, and then again I am in this line, is the most important line, where I'm summing the discriminator LR loss between real B and valid, and also between fake B and fake, and just summing them, and then do back prop and step. That's all. That pretty much my training ends, and the next few lines here is just for logging purpose. That's not really part of training. It's just for visualizing how my training is improving batch by batch, or rather epoch by epoch. So basically I'm just calculating total batches done till now by multiplying the current epoch with the lane of the train data loader plus the current index. And here I'm just printing the various components of my training, that is loss DVA, loss DLR, all these things. And finally here my those utility function that we just discussed some time back, that is sample images, will return me the path of the created images from my validation data set, and then visualize output will just visualize or plot those samples, that is both the original validation dataset and the corresponding generated dataset for the validation part, and plot it in my notebook. So I think this plot is it's running after only one epoch, and after running quite a few epochs, I think 20 or so, I was beginning to get some realistic looking images from the dataset, and these were my those output. And again, a point to remember on the dataset, that this dataset that we have used in this notebook is this maps.tar.zz. It's a very famous one from UC Berkeley, and that was used famously in the Pix2Pix dataset. And the actual dataset is something like this. So I have 2 folders in the dataset, train and validation, and the train folder has, I think, 1097 number of images, and validation has 1098, and each of the data is like this. So the dataset comprised of satellite images of New York and their corresponding Google Map pages. The image translation problem involves converting satellite photos to Google Map format, or the reverse, that is Google Map images to satellite photos. And all the images have a digital file name, and they are in JPEG format. Each image is 1200 pixel width and 600 pixel height, and contains both the satellite image on the left and the Google Maps image on the right. And that pretty much wraps up this video. The GitHub link is in the description. That pretty much wraps up this video, and the GitHub link is in the description. And finally, over the next couple of months, I will do many popular GAN or generative adversarial network implementation from scratch with PyTorch. So stay tuned and do subscribe. Thank you very much for watching. See you in the next one.